Hello everyone, I am Lalit Rai, BTech third year electrical engineering student of IIT Palakkad. Today I am presenting my digital signal processing course project, in which I have to design and implement high-pass FIR filter using window technique with given specification. Cutoff frequency of 1 Hz, sampling rate of 360 Hz, stopping attenuation is 40 dB, and ECG signal. What are ECG signals and why do we apply filter over it? These are the signals which reflect the electrical activity of heart observed from the strategic point of human body. The ECG signal contains essential information about the cardiac pathology affecting the heart. Therefore, detection of each section of the ECG signal is essential for health professional in screening, diagnosis, and monitoring of several heart conditions. However, detection and discrimination among ECG sections become complicated due to the variable physiology of the reference point, mainly produced by cardiac abnormality, alteration of the isoelectronic lines, or noises added to the ECG signal. Therefore, to improve diagnosis of heart diseases from ECG information, all these corruption problem must be addressed, and for that we require filters. Filters. In the field of signal processing, we consider filters as devices that suppress unwanted components of features from a signal. If we try to elaborate them, then the two main functions of the filters are signal separation and signal restoration. Filtering operation can be done in two ways, with the help of analog filters or by digital filters. Analog filters, they are electronic circuits made up of active and passive elements. They are designed to operate on continuous time signals. While digital filters, we can understand them as the signal processing system, which basically perform mathematical operation on discrete time digital signal. That's why they are highly accurate. We will mainly focus on the digital filters, their design and implementation. We have studied in the class that we can express the relationship between input and output using difference equation that we have shown here. One can also apply discrete time convolution to obtain the output of the system when the system is LTI. There are various methods by which one can perform the discrete time convolution, which are listed below. Ordinary linear convolution, matrix method, tabular method, circulation convolution that we have discussed in the class also. In this project, we have used cyclic convolution that we will discuss in the later part of the project. Assuming all the initial conditions of the systems are 0 and taking the Z transform of the Xn and Yn, we can define the transfer function of the digital filters as Hz equals to Yz divided by Xz and represent the digital filter in the Z domain as shown below. We can also convert the transfer function Hj into digital frequency response by mapping equation. The magnitude, frequency response, and phase response are shown below here. Types of filtering operation. The basic filter types can be classified into 4 categories, which are as follows: low pass, high pass, band pass, and band reject. Generally, the filters are designed based upon the specification. That is, for a given pass band, stop band, and transition band of the filter frequency response. The filter pass band is the frequency range with the amplitude gain of the filter response being approximately unity. The filter stop band is defined as the frequency range over which the filter magnitude response is attenuated to eliminate the input signal whose frequency components are within that range. The transition band denotes the frequency range between the pass band and the stop band. The magnitude frequency response for the high pass filter is demonstrated in the following figure. Here. All the above mentioned digital filter can be implemented using FIR, that is finite impulse response, whose impulse response depends on only past and present output. We can implement the digital filter with both FIR and IIR. IIR are infinite impulse response, whose impulse response depends on past outputs or also along with the past and present inputs. These are the some of the methods by which we can implement the digital filter using FIR and IIR techniques. We will use only linear phase FIR filter using Windows here in our project. Finite impulse response FIR filters. To implement the filter required in our project, we will mainly focus on FIR filter design. An FIR filter is completely specified by the following input-output relationship. Here, all the 8 terms are eradicated. Applying the Z transform on both sides of the equation lead to Yz equals to V0 xz, V1 Z inverse xz, V2 Z power minus 2 xz, and so on. And its transfer function can also be represented as Hz equals to Yj by Xj. FIR filter realization using window method. As we all know that ideal selective filters are non-causal and are not absolutely summable, which means they are practically non-realizable and PIPO unstable. Also, the sudden truncation of the infinite length coefficient sequence develop the undesirable Gibbs oscillation. To deal with both the above mentioned problem, we will use window method. We use a window which is symmetrical, that is defined from -m to m, to gradually weight down the coefficient of the designated FIR filters to 0 at both ends. Given below are the window function for FIR filter design. Now we will apply the window sequence for the filter coefficient to obtain the window impulse h of wn, which is equal to the multiplication of filter coefficient h of n and window sequence h capital H wn, where -m to m equals to n minus 1 by 2. HWN we can find from here and HN we can find from here. As we've already discussed in the Z domain, the transfer function is represented as yz equals to hj into xj. Therefore, we have the freedom to obtain the output through any form. Either we can directly multiply the obtained transfer function to the Z transform of the input signal to obtain the output, or we can do the discrete time convolution. We also learned in the class that the circular convolution of the two discrete time signals correspond to multiplication of their DFTs. And DFT of a discrete signal is equal to Z transform evaluated on a unit circle. Therefore, we can write Yn as Yn equals to circular convolution of Xn and Hn. Circular convolution. The formulas for circular convolution we have mentioned here. In circular convolution, because we have different number of elements in Xn and Hn, therefore we will use zero padding. Since we have developed all the required concept to design the required high pass filter, now let's move to the designing of it. Problem statement: designing and implementation of high pass FIR filter using Windows technique with given specification. As we have already discussed, to obtain the window impulse response, we will use Hn and capital HWN and multiply them, and will found the coefficient B0, B1, Bm of the transfer function. We have proved in the class that the circular convolution of two discrete time signals correspond to multiplication of the DFTs, and DFTs of a discrete time signal is equal to Z transform evaluated on a unit circle. So we can define Yn as circular convolution of Xn and Hn. This is the source code that we have used in the MATLAB. We have defined for n equals to 151, omega equals to 0.0174, that is 2 pi f into cutoff frequency by sampling. Here we have implemented the for loop to find the coefficient, that is capital HWN and Hn. Here we have used the circular convolution. We are finding the length of the input signal and of the filter. Here we are padding the zeros to make the elements number of elements equal. And now we are performing the summation here by running a for loop. Here we are plotting the graphs only, nothing else. Using the above MATLAB code, we have found these graphs. This is our unfiltered input. You can see that the sinusoidal function in it. Now we have applied the magnitude, our high pass filter. This is for n equals to 151. You can see that the sinusoidal graph is getting flattened. You can see here, this is the unfiltered signal, this is the filtered signal frequency spectrum. You can see that the 1 Hz frequency spectrum is gone here. As we are increasing the n, we are taking n equals to 181. You can see that the output is getting more flattened. We have found the output using inbuilt and the cyclic convolution function and match them. They are almost equal. There is another frequency spectrum for input signal and output filter signal. That is for 181. This is the GUI that we have found for n equals to 101. This is for n equals to 330. Observation that we have made, we have plotted the frequency spectrum for both filtered and unfiltered signal. As the filter we have applied was a high pass filter of cutoff frequency 1 Hz, we can see that the spectrum below 1 Hz frequencies got disappeared. Also in the time domain, we can see that after applying the high pass filter, the signal has lost its sinusoidal form and we are increasing the window length, it's getting more and more flat. With the given specification, we have observed that at n equals to 181, we are getting the closest possible result. Thank you.